Complete. Seems to be recording. Okay, so let us start. Okay, so Kavita has described some parts of cones and cone programs, cones and dual cones to you. I'll be discussing cone programs, which is not exactly continuous in that chapter. So there are several parts, several sections in between, but somehow it's possible for me to tell you about cone programs without needing to rely on those parts. And when Kavita resumes next week, she will do the parts before the cone programs. And then after cone programs, whatever you talk about in duality of cones will be used to prove the strong duality theorem for cone programs. Okay. So, yes, the chapter looks like initial discussion on cones, dual cones, and then cone programs, and then cones and dual cones together with one fact, which we will reach at the end of today's discussion, will be used to prove the strong duality theorem. Okay. So I'm doing the middle portion today. Okay. So I want to tell you about cone programs, and I want to motivate them from using linear programs. So here is a linear program. It's all a little congested on this slide. But, yeah, so you might recognize this as a linear program, except this is a slightly non-standard way of writing this inequality. We usually write AX less than or equal to B, but if you take this AX to the other side, you get this. So another useful way of thinking about it is B minus AX is the vector of slack values. For each equation, the slack values. And what we are saying is that the slack values better be greater than or equal to 0. So if you had introduced slack variables and set up the inequality here that all the slack variables should be greater than or equal to 0, that would amount to basically this. Okay. But the point I'm trying to make here is that there seem to be two cones involved here. One is X is greater than or equal to 0. What does it mean X is greater than or equal to 0? We are actually in n dimensions, and to say that X is greater than or equal to 0 is to say that X is in the positive orthant. Yeah, in the positive orthant. And the positive orthant is a cone, and that cone, let me call it K. So there is one restriction that X must come from a cone, and then these quantities, the slack values, must come from this cone, because again it is greater than or equal to 0. There are m quantities here, and all those m quantities simultaneously must be greater than or equal to 0. Okay. Yeah. So this 0 is a bold-faced 0, a vector of m zeros. Yeah. So there are two cones going on here. So let me just say in another way. So this cone K is where our x's come from. So we are trying to find an x here which optimizes this, but that's not all. For an x to qualify as feasible, we compute to that x this affine form B minus AX. Yes, you compute this. It gives you a vector of length m. Because A is an m cross n matrix and B is also a vector of length m. So this is the n-dimensional space, the world in which X lives. On X, we perform this transformation. It takes you to this point. So if you perform the transformation to this entire cone, you might have got these objects, yeah, all living in Rn. Now, some of them pass through this cone. So those points who map into this cone, yeah, those are our feasible points. So there will be a bunch of points here, which when transformed by this will fall inside this. Yeah? They are our feasible points. Okay. And among those points, we are trying to find the one or the ones that maximize this linear function. Yeah? It's C transpose X. C is an n-dimensional vector of reals. Okay. So is it clear? This is just linear program. We are just trying to avoid saying greater than or equal to 0 and instead saying some objects must belong to a cone. This must belong to a cone and this difference must belong to a cone. Okay. Just avoiding the word greater than or equal to. So then, so it sort of gives you a way to say things more generally. So in this special case, this L, I've got it backwards, of course. Yeah. So this was K and L. K was on the left, L was on the right, and K happened to be this special cone, the positive orthant, and L happened to be this special cone. But if we ignore the fact that we have to work with these cones, but we will be happy to work with any cones, then what you get are called cone programs. So let me write it down. An example of a cone program. Same thing. Yeah, we maximize the inner product of C and X. Okay, this previously it used to be called C transpose X. X must come from this cone. And when you transform the X, you get this cone and you must fall in this region. And those values here will be your feasible values. And there is a C vector here. And among them, the one that produces the greatest value in the direction C, that is your maximizer here. Okay. So when we say cone programs, we mean programs like this, where you have an objective function which is linear, and there are two closed convex cones. Yeah, they need not be polyhedral cones. They are arbitrary closed convex cones. The X has to come from one of the cones, and the other cone acts as a filter to remove those X's which don't behave themselves. That is, you apply this affine form to it and make sure that it falls in this. Okay. So is this clear? Does this look reasonable? It is like a generalization of linear programs using cones. Okay. Now, when you write down such a program, what is the value of the program? So the value of the program is among, sorry, I should probably write more here. So among all, yeah.
Sorry, Jacob, can I just interrupt once? If I had written it in equational form,
yeah.
Would it have looked simpler?
In equational form, then L would just become a single point because we would have said, sorry, what did I do? We would have said that this basically saying B minus AX should be this very trivial cone L.
Exactly.
Yeah. So, but we will keep this in this general form. Yeah. So with equational, the L becomes this trivial cone or a very degenerate cone which consists of only one point. This will come back in our discussion later.
Sure. And in our generalized cone program, it would still have been equal to 0, or would you have generalized it to it belongs to L?
Sorry, if
so when you have,
so when I write an equational form of a cone program as equational form of a semi-definite program as a cone program, I would nevertheless call it L and say my L is
I see. I see.
Yeah, and we will do this later.
Sure.
So the final theorem that we are going to discuss today will have to make a distinction between general L's and L's of this kind. Okay, so it will come back to haunt us. So you identified the right thing. Yeah. So, all right. So I was telling you what the value of a program is. The value is basically the maximum that it achieves. Unfortunately, so we have to just say what is the supremum of this. Well, it can be unbounded. Sometimes there might be an upper bound, and there is a supremum. Yeah. So, but it's not always achieved. Okay. So unlike linear programs, we've already seen in semi-definite programs. So semi-definite programs can also be formulated as cone programs. By now, you probably can imagine how it is done. So we have seen that there are semi-definite programs where there is an optimum, but there is a value which is bounded, which is finite, but it is not achieved. Yeah, you can approach it, but you cannot achieve it. Okay, but if you can achieve it, then we call the solution that particular x whose image lies in this cone under this b minus ax transformation. Okay, that one will be called an optimal solution. Yeah, so as I was saying, there are cone programs with finite value but no optimal solution, and let us see an example which is the same old example. So I'm going to claim that this is a cone program. So let us see in what way this is a cone program. So but let us first ask what is the program. So we are trying to minimize the quantity x subject to z equals 1 and z squared greater than xy. So Kavita, last time you told them about the toppled ice cream cone.
Yes. That was the last thing we did.
That's the last thing we did. Okay. Yeah. So I hope you have a fair idea of what the toppled ice cream cone looks like. I will try and see if I can show you a picture on my computer. But right now, it's an object in 3 dimensions. X, Y, and Z are our variables, and it satisfies this equation. Yeah. So I'm sorry, did I get this wrong?
Yes, it is xy is at least z square. Yeah. Because the determinant of the 2 cross 2 PSD matrix should be non-negative. This is correct. Yeah.
So I might have made the same mistake many times. Okay, so please watch out. Yeah. So this particular cone, yeah, and z equals 1. So okay, so let us just see in how is this a cone program? Okay, so we can say that the point that we are trying to, so let me just try and write things down. Yeah. So what is the cone K? K is this toppled ice cream cone. Yeah. Now we have this equation. So we will write this as the matrix which extracts the Z out of, maybe I should write 0, 0, 1 and maybe a minus here. Yes. So yeah, and my B, it's no space. Yeah, let me just write B. B is, so we are in 1 dimension. B is just the vector 0. Okay, and L is, so if I write B minus A, the points are X, Y, Z belongs to L, which, oops, B should have been 1, or I should have prepared this before. So suppose I say 1 minus AXZ belongs to L. Yeah, here. What does this mean? 1 minus AXZ with this value of plus. Yeah. So if I do 1 minus AXYZ, this will become 1 minus Z, I hope. Yeah. And then belongs to L, but my L is 0. That means basically I'm restricting myself to Z equals 1. So this particular equality Z equals 1 has been written in this perverse way. Yeah. But now at least we have two cones going for us. This is the toppled ice cream cone, and this is that trivial cone, which we need to use when we have equalities. Okay. Is this clear? So although I have not written it explicitly in the cone program form, this can be cast into a cone program by using these objects. Okay. Now, you see, subject to Z equals 1, and yeah, so you can, X times Y has to be at least Z square. So the left hand side here is 1. So how small can we make X? We are minimizing. How small can we make X? So we can make X arbitrarily small. I can make it 1 over 10 and choose Y to be 10, or make X to be 1 over 100, make Y to be 100. Okay. So for any small value of X, we can take Y to be 1 over X, as long as X is greater than 0. So you can see that within this system, we can make this X go down as much as we want, but never quite touch 0. Okay. But if this were cast as a maximizing problem, so if this was a maximizing problem, I would have put a minus X here. But anyway, so the value of this cone program is 0. Okay, because we use supremum for maximization. Okay, so we will use an infimum for minimization, and you will get 0 as the value. But you can see that no optimal solution exists. You cannot simultaneously have Z equals 1 and X equals 0, because this will be violated. There is no feasible point where the optimum is achieved, but it can be approached. Okay, so this was an example. So now I want to define a notion of a sequence. Yeah, so this business of approaching. Yeah, so we are going to turn. So far, we were within the cone, within the feasible region, and we were trying to minimize. And in the process of minimizing, we were approaching an optimal point, which doesn't exist. Yeah, so we approach the point, but we stay within the feasible region. What we are going to do now is we are going to think about points which are not actually feasible, but they approach feasibility. Okay, so we say that a sequence. So you have a sequence of points in K. You remember K was the first cone. So there is a point in K, but being in K is not all. The feasibility involves two things. You have to be in K, but your image under this has to be in L. Okay. So we are going to take a sequence of points which are in this cone, but they are not necessarily inside, they're approaching this cone and eventually get arbitrarily close to this. So let me just explain how it is said. So a sequence, yeah, so these are points on the left-hand side, on inside the left-hand cone. Yeah, the left cone. Yeah. And we say that such a point, such a sequence is feasible. Okay. Yeah, so it's probably a wrong thing to say. None of these points are necessarily feasible. Yeah. This sequence is said to be feasible if you look at this quantity, b minus axk, as you move on this path inside k, it comes arbitrarily close to the cone L. And how do you say that? There are these points, so-called tracking points, so-called because I'm just using the word tracking. Yeah, these are the tracking points inside L, and the distance between this and this goes to 0. So let me maybe draw a picture. Maybe it's clear to you already. Yeah, so this is the cone K, and this is the cone L. Now I'm taking a sequence of points. Say this. Yeah. So I'm taking a sequence of points here. Yeah, going in this direction maybe. Now as I move in this direction, these points, these are the points xk. Yeah, the points xk here. So as I move in this direction, the image under this operation, they give these points. Sorry. Yeah. And as you can see, what I'm trying to suggest is that these points are approaching L, but we make it more explicit. We say that there are these points xk prime. So they are the trackers here. Maybe I should. Some other language. So there are these trackers, and the distance, this distance between them in the limit goes to 0. Yeah. So we don't say that this eventually falls inside L. It doesn't necessarily fall inside L, but there are points inside L which come arbitrarily close to it as k goes to infinity. If such a sequence, such a set of points can be found here, yeah, this xk prime, don't pay too much attention to it. It's just an artifact of the way the definition has been written. Basically, we should be able to travel in this cone k and give, I mean, yeah, so show that we have the right intentions. That is, we want to get into L. Okay. And if we get arbitrarily close to L, then we are going to call this sequence a feasible sequence. Okay. So in particular, if you already have a point here whose image lies inside L, then there is no problem. You could just repeat it. Yeah. And you can just, for this tracking points, you could just take its image here again and again and again. And that would become a limit feasible point. Yeah. So I should probably say is limit feasible. Yeah. It's feasible in the limit. Okay. So this is the notion of a feasible sequence. Yeah. A sequence is said to be limit feasible if this happens. Are there any questions? So did I write this again wrong?
No, this is correct.
So now you see, again, I have written a cone program, and it's very similar. I'm not going to explicitly, or maybe I do later on. Yeah, but there is this cone here. Yeah. Now I would like to describe this cone to you. Okay. So let us look at this equation. I don't know how much time was spent on this equation last class. So when z equals 1, what can we say about x and y? Well, x and y lie on this hyperbola. Yeah. When z equals 2, sorry, what is going on? Yeah. So imagine this is equal. Yeah. So when z equals, if you fix z equals 1, the values x and y which satisfy this are to the right of this hyperbola. Okay. And when z equals 2, they are all points to the right of this black hyperbola, and so on. Okay. And then when z is half or so, there is this hyperbola. When z is 0, yeah, when z is 0, we get a very degenerate situation. If z is 0, then x, if you look at equality here, then either x has to be 0 or y equal to 0. So when z is 0, we get everything to the right of this. So I have not drawn the z-axis. There is a z-axis, and you should think of this as something that is rising. Yeah. When z equals 0, you get all the points. When z equals 1, of course, you are raised because z is 1. And at that level, if you had sliced this object, that would have led to this cone. So there is a cone here. Yeah. There is a cone here. And that cone is being sliced for various values of z. And each time that cone is sliced, a particular contour like this shows up on the. Okay. So that is one way of thinking about the toppled ice cream cone. Okay. Now, if you look at this particular program, which says z has to be equal to 1. Yeah. So we are z equals 1, meaning this is our feasible region. And y has to be equal to 0. Okay. So I'll let you imagine how you will write. Okay, we will very soon write this in the standard form of a cone program. But right now, just focus on these inequalities and equalities. Yeah. So clearly, this is infeasible because the moment y equals 0, the right-hand side here becomes 0, and there is no way z can be 1. Okay. So this is infeasible. But it is actually limit feasible. Yeah, this particular cone program is limit feasible, and let me just explain. So how do you write this as a cone program? One way of writing this is assuming that we are in 3 dimensions. Yeah, so our points are 3-dimensional. So our cone on the left hand side, this cone, sorry, this cone is the ice cream cone, which has been written here, the toppled ice cream cone. And then we extract, see, we have to impose these conditions. So we extract the y coordinate and the z coordinate. So if I multiply this by x, y, z, y and z will show up here. Okay. So that is our A. And then I say that it must be equal to 0 and 1. Yeah, y must be 0, z must be equal to 1. And so we are now working in the right-hand cone. The cone L is in 2 dimensions. So, and it consists of only 1 point, as we have been discussing. When you have to impose equality constraints, the other cone consists of a single point in Rn. Yeah. So the single point in this case is this 0, 0. And now if I write, yeah, so if with these, if you write the cone program, that will exactly correspond to this situation. Okay. Now, let us, I would like you to think about what is happening here. Yeah. So how are we, the claim is that this particular cone program, which is infeasible to begin with, admits a feasible limit sequence. And the point is this, that if you look at these, yeah, so which are these points? So you understand, when I draw this curve is raised above my paper. Huh? This is at z equals 1. Yeah. So it is raised above the paper. So what does a typical point on this line look like? Well, x takes a value k, y takes the value 1 over k, and z takes the value 1. Okay. So a typical point looks like this. And now, as you keep traveling on this line in this direction, the value of the only problem here is, okay, so let me try and move in this direction. Okay, and let us ask what is happening to these constraints. Whenever I'm on this line, certainly this constraint is being satisfied with equality. Yeah. X and Y are greater than or equal to 0, no problem. Z is equal to 1 because I'm traveling only on this slice, which is Z equals 1. Only trouble is, so everything is good. This Y is not quite 0, but by moving farther and farther and farther away, I can get closer and closer to Y equals 0. Okay, so that is what is being done here. So so my cone, the right-hand cone, L, consists of only one point. So what I used to call xk, I'm calling pk. These are the points. The tracking point is always 0, 0. The points that I move on, as I move on that curve, are k 1 over k1. Yeah, z value is 1, x value is k, y value is 1 over k. And now, if you take this difference, yeah, between, so if I project this point onto the last two coordinates, I will get a 1 and 1 over k. So when I subtract this, the 1 here and the 1 from this, which comes out of this, will cancel and give me 0. And this 0 minus 1 over k, I missed the minus sign, I think. Yeah, never mind. The point is that as I take k large, this 1 over k here is going to go to 0, and I'm getting to 0, which is what my definition demanded. I should be able to give tracking points. The tracking points were 0 in this case because the entire cone itself has only 1 point. And this quantity should become 0 eventually. This quantity already had a 0 in the z coordinate. The only problem was the y coordinate used to be not quite 0, but a small number, 1 over k. And by taking k large enough, I will approach 0 arbitrarily close. So this is a program which is not feasible, but it is limit feasible. Okay, questions?
And what value would this cone program return? What solution would it return?
So it doesn't return a solution. We just say, say the value of the objective function.
It would say infinity is unbounded.
Yeah, yeah. So as I move along this, yeah, the value that I will get is arbitrarily large. Right now, yeah, that's it. So actually, I hadn't defined what a value of thing is. So associated with each cone program, we will, so I told you what a value of a cone program is. you live inside the feasible region. Yeah. So when you say value of a cone program, you are very particular about feasibility. Yeah. The point has to be in K, its image has to be in L, and among them, what is the maximum, supremum that you can achieve? Yeah, you can reach. Yeah, as you move inside the feasible region. That is called the value of the program. But now we are going to talk about limit value. Limit value, as you can imagine, is what Kavita just asked. That is, if you have a limit feasibility, what is it called? Yeah. So if you have a sequence like this, which is feasible, yeah, which is limit feasible, then that sequence, as you move along it, will give you some value for the objective function. Okay. So you consider all possible limit feasible sequences and you compute this quantity. Yeah. I don't know whether this should have been a lim sup or a lim, but it doesn't matter. And whatever you reach at the end. Yeah. So the limiting value of the objective function as you're moving inside this sequence xk. Yeah. And among all those xk's which are feasible, choose the one which gives you the best. Okay. That is called the limit value of the cone program. Okay. Now it turns out that there is a limit issue here, but this supremum over them, there is I don't know, some diagonalization type of argument. Suppose you had many sequences, each of them reaching a bigger and bigger limit. Yeah. Then what you could do is perhaps travel on the sequence like this, and then there'll be a single sequence which will reach this supremum. So this supremum is achieved, yeah, but of course here it is still a limit situation. Is this clear? Is the limit value of a program clear? Yeah. So once again, we had this picture of tracking points. So you move in this direction and you have an objective function C, and the maximum that you can reach as you move along this, that is called the limit value of this sequence. And this sequence is a feasible sequence if it is moving with the right attitude on this side. And among all feasible sequences, you find the one which achieves the best along this direction C. That is called the limit value of this cone program. Yeah. So we will see some examples now. Okay. So note that the value of a cone program already has, it's not something that is always achieved. Yeah. You might have to only approach it. Okay. So the value already has, at least from our, old-fashioned linear program days, there is already a source of discomfort. Things are not achieved, you approach them. And outside, it's not entirely from outside. The X still stays inside the cone K, but the image is approaching L from the outside. And by using such sequences, you get to some values. Okay. So those are called limit values. Now, I want to just give you an example. So the whole point is this, that the limit value and the value for a cone program need not be the same. Okay. Yeah. In both of them, we have made, what should I say, some compromise. Yeah. In the sense that we are allowing approaching instead of being exactly feasible or exactly taking on a certain value. But the two compromises have different characters. Okay. So in one of them, you get the value of the cone program. In the other, you get the limit value. Okay. And there are cone programs which are feasible. Yeah. But the value is different from the limit value. So let me just give you an example. So, okay, so this was the definition of limit value. Does anybody have any questions? So consider this cone program. Yeah. So this point should be in the toppled ice cream cone. Yeah. And why this is a cone program, we can see, we'll see. Yeah. But look at this. Yeah. So we are looking at all points whose y coordinate is 0, and they must belong to, let us say we are looking at all points in r plus to the power n. Yeah. Sorry, what n? It's r plus 3. Yeah. So all points x, y, z in the positive orthant, let's say, and with the property that when you project them onto, yeah, so you take these two coordinates and set this to 0, then it should be in the toppled ice cream. Now, the point is that if a point like this has to be in the toppled ice cream cone, you remember x times y is on the right hand side and z squared is on the left hand side. So if one of these is 0, z has to be 0. So if you look at the biggest that z can get, if you insist that y has to be 0, yeah, if you insist that y has to be 0, you have no choice, z will have to be 0. So the value of this particular toppled ice cream cone is 0, the value. Yeah? Now, what about the limit value? Well, actually, the same picture still works. We could travel along this. Yeah? We are inside our cone K. This is our cone K. Yeah? The entire three-dimensional orthant, positive orthant. And let us travel like this. Yeah. So what, as we travel like that, we approach points like this. Yeah. X, Z, this quantity, if you parameterize it right, then this is something like 1 over K, and this goes to 0. That means take any value of Z, we will be able to get eventually to something that is very close to. So you can imagine, so I don't know if you're seeing the same picture of the cone that I'm seeing. I'm seeing a little, what should I say? A little mountain here, like that. Yeah. That is, these are all slices of that mountain at various heights, Z, which I have not drawn. And as I move, yeah, now I will let you imagine that it should be possible for me to move, yeah, or rather something like that. Yeah. So that as I keep going, so initially I have cut the blue line. Then when I cut the Z line, the red line, I get Z equals 1. Then when I cut the black line, I get Z equals 2. Then at some point I will cut, even this horizontal line here would cut all these hyperbolas eventually, because all these hyperbolas are going to asymptotically settle on this line. So I can presumably increase my values just, sorry, while reducing the value of y. If I do it at the right rate, I will be able to touch all these hyperbolas. That means as I move along that line, yeah, as I move along that line, I will hit arbitrarily large values of z. So what do you think is the limit value of this cone program? Somebody? I want to move in the positive orthant, but I want to make the y coordinate go to 0. So I'm going to approach the y equals 0 line, but I should step on points where I'm in the ice cream cone, yeah, and the corresponding z values are as high as possible. Yeah. Sorry, what should be the limit value? I don't know if what I was trying to say here makes any sense. So I
Is
want to
that
climb.
unbounded?
It's unbounded. I want to climb this mountain. Yeah. But I'm climbing this mountain in some strange way, like this, so that I'm reaching higher and higher heights, but I'm getting closer and closer to this wall. You know, this XZ plane. XZ plane is this plane. Yeah. And I'm getting closer and closer, but actually climbing in height. So this wall, this cone here, yeah. Yeah. So I'm going to climb higher and higher and yet get closer and closer to this wall. So since I'm climbing higher and higher, as somebody pointed out, Z is actually unbounded. So explicitly, yeah. So let me say that my original cone K, yeah, K was R plus to the 3, yeah. And the toppled ice cream cone is my L. And let me say that this is my, keep making this mistake. Should I write a minus or a plus? Because there is a minus already in my equation, B minus AX, yeah, equal to 0. Yeah. This B is this B. And this equal to 0. No, sorry. So I think minus was B minus. Minus was probably correct there. Second, I don't know why I made this mistake. So if I take a point, typical point X, Y, Z, and apply the matrix A to it, yeah, and I do B minus AX, Y, Z for this value of B, yeah, the value of B here, then I basically get X and Z, the 0, okay. So I walk along this curve. Yeah, so why am I calling it a curve? This set of discrete points, of course, but as k rises, these points change. But the important thing is, look at the z coordinate here. This z coordinate is increasing unboundedly as k is increasing. Okay, but that I could always have set up some fake points where the third coordinate rises. But look at what happens if I apply this. It looks like X. Yeah, so if I look at this quantity will look like yeah. So if I apply this to this, I'll be left with k cubed 0 k. Now k cubed 0 k is not a point in the toppled ice cream cone, but there is a point close by in the toppled ice cream cone, namely this. And as k increases, this point and this tracking point, they differ in 1 over k. So as k goes to infinity, the difference here goes to 0. So this is a valid feasible sequence. This sequence of points is a valid feasible sequence, and k is going unbounded. So whatever you said intuitively of thinking about climbing this mountain in a slightly strange path, yeah, that is borne out by this formalism, and you get what you intuitively thought to be the correct answer. So here we have a situation where the value and the limit value are different. Yeah. So value is somewhat rigid in the sense that it insists on feasibility. Limit value is somewhat, what should I say, more relaxed. Yeah. And it allows you to achieve greater values. But I mean, why are we getting into value, which will be discussed later? goes through limit values, because unfortunately the cones of say that arise in semi-definite programming, etc., are not as nice as those that arise in linear programming. So, but in the end, which I will tell you at the end. Now, are there any questions? Okay, so the book, this very same problem, it thinks of it, the ambient space as R2. I thought of the ambient space as R3. You can think of the space as R2, different cone program to capture this very same thing that has been written here. And I will not do this. So you can check that that also gives you the same unbounded value for the limit value of the cone. So that other formulation of the cone program also gives you an unbounded value. Okay. But here we have a situation where the value and the limit value are different for the cone program. And turns out that this was because these cone programs were in some ways degenerate. Actually, although I shouldn't say it is degenerate, often such things happen. Okay. Because you are really slicing off parts of the cone, and then they become very skinny objects. Okay, and because of they become very skinny objects or degenerate objects, you are not able to find a point inside them, but you are only able to approach them. So anyway, I don't know what I said and why it makes sense. But the point is that if you have interior points, yeah, if the cone program admits interior points, then this cannot happen. The value and the limit value will be the same. The value that you get by staying inside the feasible region and the value that you get by taking liberties and moving outside and trying to approach the cone L from outside, those two values will be the same. Okay. So this is the theorem. But before that, I have to tell you what an interior point is. Okay. You already know from your idea of real numbers, etc., what interior points are. But what I'm going to describe now are interior points of cone programs. Okay, so let me, yeah. So the objective function plays no role. What is an interior point of a cone program? That's what I'm going to tell you. And then I'm going to tell you the theorem. Okay, theorem which formalizes this. Questions? So we have this cone program. This is what we started with this morning. You're trying to maximize something subject to something being in L and something. Okay. Yeah. So so what is an interior point of this convex program with this cone program? Yeah. So it is a point X. So it is a feasible point. An interior point is a feasible point, but there is wiggle room around that point. Yeah. Now, what do we mean by wiggle room around that point? There is some, some scope for perturbation around that point. So now that we, as Kavita had guessed, we need to make a distinction between this special kind of cone on the right hand side, which consists of a single point, and other kinds of cones which have an interior. Interior means, so there is a point inside so that an entire m-dimensional ball can be put around that point. Okay. So let me start. Let me tell you what the definition of an interior point of a cone program is. It is a point which is feasible, and that point itself is in the interior of the cone. That means there is a ball around this point X, which is contained inside this cone. This is the definition we will use when the target cone on the right-hand side is not full dimensional, but just a point, yeah, just the 0 point. Then the point on the left-hand side itself should be in the interior of this cone. Okay. If the cone on the right-hand side is full dimensional, then what we ask for L, this point which is inside L should have a little ball surrounding it, which keeps it inside L. Okay, so let me show you the pictures here. So this X tilde here is my interior point of the cone program, interior point of the cone program. So suppose your cone was not the 0 cone, the trivial cone consisting only of the point 0. Okay, that will be dealt with here. Yeah, so don't look there. Yeah, just look here. This is the second case I'm discussing. Okay. Then you take this point X. This point, if you do B minus AX, X tilde, X tilde, X tilde. So if you take this and you get this, maybe I should just. So this point here is where this maps, but there should be a ball around it. That means this point should be in the interior of this cone. That is, there should be a ball around it, which is entirely contained in L. Then this point is called an interior point of the cone program. X tilde will be called an interior point of the cone program. Yeah, we don't insist that X tilde itself should have a ball around it or anything. The target where it maps into L, there should be wiggle room there. There should be room available there. Okay. That is this case. If your target cone is just L, there is no hope of having a ball like this on this side. It is just a single point. Okay. In that case, we insist that there should be a ball available here. So when is X tilde called an interior point? In this case, there is one consideration. In this case, another consideration. These are related, but when we finally try to prove theorems using the fact that value and limit value are the same for certain cone programs, neither of them by itself will cover all the cases that we are interested in. Okay, so we make these two distinctions. In this case also, we are able to prove there will be an argument which will allow us to prove that the value and limit value are the same. If this happens, then also we will be able to prove that that is just because we wanted one definition to capture two of them. There are two things that we will be doing. We'll be considering cones where L is not just the 0, and there'll be cones where there is an equational form which forces L. Okay, so then the theorem is the following. Suppose you have a cone program. This is the same thing I write again and again. Actually, I just copy. Okay, and suppose it has an interior point. Then value equals limit. That is the theorem. And in the remaining half an hour, I would like to prove this theorem. Is the question clear?
So Jaykumar, you were referring to the dimension of L. So L could be, need not be full dimensional. It need not be just a single point also, right?
Sorry, but I'm not able to hear you.
Oh, sorry, the connection.
Sorry, I was not able to hear. No, I don't know where the connection is. I'm also on a wireless. So you said we are referring to the dimension of L. Please go ahead.
Exactly. So are these the only two cases, that is either full dimensional or?
No. It is possible that, thank you. It is possible that L could be a very flat cone on this side. Yeah, it could be on a sheet of paper Although you are on m dimensions, it is sitting like a cone which is inside a plane. Yeah. Or it could even be a subspace or something. Yeah. In that case, we don't have an interior point. Yeah. So if L is not 0 and L is somehow which doesn't even admit a ball inside it, an m-dimensional ball inside it. Yeah. Then this all our theorem is not applicable in that case. Okay. So it's not as if we have covered all the cases or anything.
Thank you. Thank you.
So there are these two cases in which we will be able to get by. Okay. That's it. No, I mean, ideally we would have liked to just stay with this, but then since we have written so many cone programs where the right-hand side is just 0, one might ask, what is the point of proving a theorem like this when it is not applicable to most of the cone programs I'm going to write? Okay, so it's not hopeless in that case also. In that case, when L is 0, you still can prove that value equals limit value in certain cases. In that case, you better have a ball on this side.
Sure, thanks.
So once again, so I would really, I mean, yeah, you probably, I've been shouting at you for an hour and you're probably tired, but this proof needs you to concentrate a little bit. I have tried to draw pictures for everything, but I also sometimes worry if my pictures make sense only to me and to nobody else. But let me try nevertheless. Okay. So once again, this is my cone, a cone program, and the assumption is it has an interior point, and then our conclusion is going to be this. So basically, we are going to say that there is a limit value. Yeah, let's say gamma. Then the value of this P, we should be able to show a sequence of points which takes value, limit value minus epsilon for every epsilon. Okay. So let me write it down. So our goal will be something like this. We'll try to show that value of P is greater than or equal to limit value of P minus epsilon for all epsilon. Okay. And from this, because limit value of a program is anyway, is if it is bigger than this for every epsilon, then it better be greater than or equal to limit value of P. Okay. But our strategy will be, we will fix an epsilon, we'll fix an epsilon greater than 0 and show that there is a sequence of points which is feasible. We are going to be honestly feasible. We are going to construct a feasible point whose value will be at least the limit value, which might be achieved by points which are not even feasible. Okay. And yeah, that limit value minus epsilon. And you are free to choose your epsilon as small as you possible. And then our argument will show an existence of a feasible point which achieves at least this much. Okay. So this is the usual way of showing things when limits are involved. Okay. So I'm first going to do, I shouldn't have written this. I don't need this. I just mean an honest 0. Yeah. So this is the second case. Yeah, the second definition here. So there is an interior point and L is not this, L is of this kind, which is a fattish cone. Yeah. So there is an L here and there is, this is our K, and there is an interior point here. What do we mean by this is an interior point? Just I'm repeating the definition. If you look at its image, there is a little ball here. Can you see? Yeah, there is a little ball here around B minus AX tilde. Okay, that's what we are assuming. And as I said, limit value is achieved. Yeah, that supremum is achieved. I said, you do some diagonalization type of. Yeah. So there is this sequence xk, which is inside this cone K. But if you look at its image here, it is going like this. Yeah. And this particular cone, when you look at its image on this side, it is something like this. Image, what do I mean by image? Image under this operation. Yeah. B minus AX under this affine transformation, you can call it. Yeah. Okay. But this point, this, as you move along this, you are moving like this here. But you are coming arbitrarily close to L. And as you are moving this X here, you are achieving a certain value here. And that is the limit value of this cone profile. And now I want to show that there is a point here, or there is a point inside the feasible region whose image is also inside the feasible, inside L here, which achieves whatever this fellow achieves minus epsilon, maybe a little bit less. Okay. So now the idea is this: what do we have? We have this X tilde, which seems to be nice on this side. Yeah, its image seems to be nice on this side. So what we are going to do is we are going to shift these points xk in the direction x tilde. X cones. Yeah. These are convex cones. So I can take a convex combination of each of these points xk as I'm moving on this line. As I'm moving on this line, at each point, I can push the line, this dotted line, slightly closer to x tilde. And how do I do that? I define a new point wk, which puts a small probability or small weight on x tilde and the complementary weight on xk. What is xk? Xk are these points on this line. And so I hope it's clear. Yeah, I have shifted this line. Yeah, yeah, maybe slightly inwards. Yeah. So what are we going to show? We are going to show that these points actually are eventually going to become feasible. That is, if you look at the image of these points, so as these points are drawn towards x tilde, their images will be pulled towards this point. Okay. And because we have a solid ball here, solid by solid, I mean, a ball, full dimensional ball here, we will be able to demonstrate that this pulling actually pulls it into the cone. Okay, that's all. Yeah. So that is the first point. So you can choose your eta initially as small as you wish, a positive number. Then if you walk along this line and construct these blue points and look at where their images fall, their images eventually will fall inside L. Okay, that is point number one. And our goal, there used to be an epsilon in our discussion. Yeah, we will do this perturbation of xk, pull it towards x tilde ever so little, so that the difference in the objective function will be at most epsilon. Okay. So somebody gives us an epsilon. We design our eta so that C with this and C with this don't differ too much. And you can see that it just depends on these two quantities, x tilde, yeah, and second. Yeah, so there might be some issue there. I will try to clarify later. Okay. So, but nevertheless, we are going to move this x tilde's inwards towards xk's towards x tilde so that it doesn't make a big difference to the objective function. And then somehow hope that this pulling here causes a pulling in the other direction here so that you fall inside it. Okay, so let me just explain. Okay, so this argument I will come back to later. Yeah, this basically says that the value of p will be at least the limit value of p minus epsilon, and then as we argued before, this basically says that the value of p better be bigger than limit value of p, because we would have proved this for every epsilon greater than 0. But okay, so we will postpone that. Yeah. Let us now see what is happening here. So I've just enlarged this picture for you. Yeah. And I'll enlarge it once more. Okay. So these black points were the X case. The purple line is these W case, which was defined above. Now, this B minus AWK, this is just an affine transformation. So if you take an average of 2 points and construct another point and ask, where does it fall? Well, you just take where the originals fell and you take the same convex combination here, and that is where it will fall because everything is linear. Okay. So the question is, why must WK eventually become feasible? And I would really like you to pay attention. The proof is just this much. Okay. So I am focusing only on this side. Clear? There is an eta. Eta has been fixed. Yeah. Eta has been fixed, and we are now looking on the right hand side, and we are trying to claim that eventually WK will fall inside this red line here. That little vein that you see there is supposed to be these quantities. Yeah, the image of WKs, and you can somehow see that that vein enters L. Okay. Why must it enter L? So let us see. So this is a picture, and I'm focusing only on the right hand side. Okay. So this was the point around which a ball was available. These YKs were the images here, images of the black lines which were kind of outside the cone. Okay, I have not even drawn the cone here. No? Just these were the tracking points for these YK. Yeah. So eventually the distance delta K between the tracking point and YK is going to become arbitrarily small. By making K large, this distance can be made arbitrarily small. Okay, keep that in mind. Let us take the average of this point and this point. That means the image of WK is here. How is this image constructed? This ZK is one second. So you take this Y multiplied by eta, this YK by 1 minus eta, and you get this point. Okay. And what is this point? You look at the tracking point and take the same for tracking. So is this picture clear? Or is everything in this picture clear? Once again, this was this point. This YK was this point. You take this YK and its average, yeah, sorry, YK and this, maybe I should call it Y tilde, yeah, Y tilde was the image of this point. It used to go there, yeah, and you take the average in the same proportion, eta for this guy and 1 minus eta for this. So this point tends to be closer to this point than this point. Okay. But just for me, do the same average for the tracking point. Now, if this distance is delta K, this distance, you see this, there is a old-fashioned high school similar triangles going on here. So the ratio of this is to this distance between this point and this point is 1 minus eta times whatever used to be this distance. Now, around this point, so I probably made a mistake. Take this point and all these points and take their average in the same proportion. Eta for this point, 1 minus eta for this point. So of course, if you did it for this Y tilde, you would get this. And if you did it for the other points, you would get a little ball here. And if this ball had a radius r, that radius will shrink to eta times r, because all these points are being multiplied by eta, And these points are, this point is being multiplied by 1 minus eta to obtain these averages. Okay. So what we know is that this point and this entire ball are inside L. This tracking point is also inside L. So this entire ball is inside L. Okay. And its radius is eta k. The distance between this and this is controlled by this distance. This distance for delta k, this is actually even smaller, but that smallness is not important. But it will be something like 1 minus eta times delta k. But as k becomes large, you see this quantity here, yeah, this distance, made a mistake, 1 minus delta, 1 minus eta times delta k. Yeah. So look at this quantity. This quantity is the distance between these 2 points. Yeah? That is going to go to 0 as k becomes large. What about the radius of this ball? This ball is going to shift. Huh? When I'm looking at a particular yk, I'm looking at its tracking point and drawing the ball here. When I look at a different yk, there will be a different tracking point and I will draw the ball there. But nevertheless, the radius of this ball is always eta times the radius of the original ball. So this is held constant and this is going to 0. So eventually this quantity is going to dominate this. That means this radius will be much bigger than this distance. That means this particular point, yeah, would also fall inside this. But what is this? To say that this point falls inside this is the same thing as saying that the WK has become feasible. Because after all, this particular point was the image of WK. So eventually this ball will maintain its size, but these will be getting closer and will fall inside this ball. Okay. And so WK is feasible. Is that okay?
So Jaykumar,
but if you didn't understand,
X prime k need not be in the interior, right?
X prime k need not be in the interior. It's just inside inside this cone. Yeah. But since I will take a convex combination of this and a point in the interior, so I will get a point midway, and this entire ball slightly shrunk will appear around that average point. That is the point I'm talking about.
I see.
No,
but there need not really be a small enough ball around X prime k inside L.
No, we are not claiming there is a small enough X prime k can be very close to the boundary of L.
Okay.
This Y is being shifted to inwards. We do perform the same shift for this. Okay. But this time when we do the shift not only with this Y, we do it with the entire ball. Yeah. That is, we try to take the average of this point and every point in this ball, which amounts to taking the average with respect to the center and then adding eta times each of these vectors to this point. Eta times, there will be a shrinkage by a factor eta. Okay. But that eta was negotiated in the beginning. Eta was negotiated in the beginning in order to keep the objective function under control. Okay. But after that, it's fixed. And now we are moving k. And as we move k, this quantity reduces. So this quantity also reduces, and eventually this point falls inside this ball. And I shouldn't say this ball, and I hope you understand. No? This is a picture at time k. At picture time k plus 1, the same thing will recur here. There will be a little ball. I don't know what a messy picture. Yeah. There will be a ball here. This distance between yk and xk prime would have reduced. And so this distance would have reduced. This fellow is about to fall in the ball. Eventually, there will become a situation where this distance has become so small that this point has actually fallen inside it. Is that okay? Yeah, I'm not sure I got across, but read the book, and or read these notes and compare them. The book doesn't have this picture, but I hope it's useful somehow. Okay. So we have maybe 10 minutes. So we are now in the other case. Sorry, please ask. Huh? There is no hurry. I don't know why I'm hurrying. Yeah. So there was this original point which was given in the definition of limit value. Unfortunately, it was not feasible because its images were perhaps always outside the cone. We move it inwards so that its image has a tendency to move towards this point. And because there was a ball here, we were able to conclude that this point eventually will enter the cone. Now we are in this situation. There, yeah. Here. Now the point is that if we want feasibility in this situation, we have to be on this point. The image has to fall on this point. What we have been given is this X case, and whose image comes closer and closer to zero, to zero, but never quite reaches it. But we have promised that we are going to show that the value is large, yeah, which means we have to show feasible points, which means we have to show points here, yeah, which actually whose image. So we actually in this case sort of do the opposite. That is, we will try to keep it inside, keep the image inside this cone L all the time, but the point. So instead of this point, these points xk, we are going to construct these points wk, which may be outside this cone. But this time we will argue that these points will eventually get inside the cone. So we are now working with k. Huh? L is a very trivial thing. There is no room to maneuver there. Good. So now, here's what we do. So recall that this A is some linear transformation which maps things in Rn to this space, which may be some big space, maybe R capital N. But look at the image of this linear transformation A. This image of linear transformation A has a certain dimension here. Okay, as Kavita pointed out, the dimension of the ambient space here could be very big. Inside that, there is this little point, and even if you take this Rn and map it, A maps it here, it might form a little subspace here. That subspace around zero, yeah. Let us say that it has dimension m, and let us call that subspace V double prime. Is that clear? Yeah. So the image under A of Rn is called V double prime, and I have explicitly written some basis vectors for it. There are m basis vectors. M is some number. Okay, need not be the ambient dimension of this space. Good. Now pull these vectors back. Yeah. So you get these linearly independent vectors v1, v2, vm, whose images under A are u1 to un. So now, see this point. Yeah. So now what I'm going to do is going to shift each of these points xk to a new point wk, so that wk's image falls right on this. Yeah, wk's image is right on L. So by how much should I adjust this? You see, if I, yeah, so once again, so you had this point xk, yeah, and if I add this, so what do? I look at where xk was mapping. Xk was mapping to this image. Yeah. So it was some distance away from feasibility. So I add to xk some amount, so that when I map this, it falls on L. Now it turns out, so once again, we have this as the basis for the image on this side. These are, we pulled them back. Yeah, so these are the vectors on the left which map to this, and these are linearly independent. So we will think of A as a linear transformation which maps these to these, where it maps Vi to Ui. Yeah. Now use that linear transformation and map this vector back. Now this object is in the image of A. Why? Well, clearly this is in the image of A because you have applied A to xk to get this. B, why is B? Yeah, in the image of A. You see, when I apply this transformation to x tilde, I fall on 0. That means B minus A x tilde is equal to 0. That means B is equal to A x tilde. So although I have written B here, this quantity B is A x tilde because we know that A x tilde is a feasible point. Okay. So I get these points zk. So these are points that I need to perturb these by. Yeah, so these are the zk's here. Perturb these by so that they start falling on this. So these are very good points now. Good in the sense that at least the right hand side is taken care of. Yeah, so here they are all falling inside on this point. The only trouble is that they are not feasible on this side. Yeah, so what I'm going to do is take these points and take their convex combination with this, which is what is being done. So take these points zk and add a little bit of x tilde to them. Yeah, whatever we did on the right hand side in the previous argument, we are now going to do with on the left hand side. Okay. So is it clear what zk was? Zk was the adjustment needed to xk so that the image of zk is y tilde. X tilde already has its image here. So if I take a convex combination, their images will always be on L. So I am safe. The right hand side we need not worry about the right hand side. We only worry about the left hand side. Okay. So what we will show is that again we will choose eta small enough so that there is not a great damage done to the objective function, and we will show that these points wk. What are wk? There were these, maybe I should draw them. There were these zk's which were constructed. Yeah, these were zk's, and I took a convex combination of x tilde and the zk's to get some points. Those were these red points, and I'm claiming that those red points will eventually get inside, and the reason is very similar because there is a ball here. You remember that ball is what saved us here. Okay, a similar role will be played by this ball. Let me now draw the picture. So now I'm only on the left hand side, just like my enlarged picture last time was referring only to the right hand side. Now I'm referring only to the left hand side. So what happens? So this was zk. You take the average of zk. You remember what zk was? Zk was the manipulation done to map it into 0. Okay, are these wk's, which are the average of this, and there is a similar triangles business going on, slightly in sort of reflected. Yeah. Now this xk previously, yeah, used to be feasible. Yes, xk was a feasible point. Yeah. So now if I take the convex combination of x tilde and xk, I get a little ball here. Yeah, because there is a ball. Okay. And as before, the radius of this ball goes down by a factor eta. This distance is the distance between zk and xk. We will see what happens to it. But this distance will be this distance hit by factor 1 minus eta. Okay. And the argument will be the same, that eventually, as k becomes large, this quantity wk, yeah, so this zk minus xk, zk minus xk, zk minus xk, zk minus xk is this quantity, which is b minus axk. B minus axk is basically the distance from 0 of this point. So b minus axk is eventually becoming 0. B minus axk is eventually becomes 0. A fixed linear transformation is being applied to b minus axk. So this quantity is eventually becoming smaller. That means the difference between zk and xk is eventually becoming, that is, this delta k, as k becomes large, is going to become small. That means this distance is going to become small. But the radius of this ball is fixed. It almost is the same. Now onward, the words I will be using will be the same. This ball holds its radius, which is at eta times the original radius here. But this distance is shrinking as I move k. So eventually, this will become inside this. So it will be here. But this was feasible. This whole ball was feasible. So this whole ball is feasible. And if this point lands up here, then it has become a feasible point. We always maintained that on the right-hand side, things are good. And once we have ensured that on the left-hand side, things are good, we are. So, yeah, so the 2 points, you choose your eta so that the first quantity, yeah, so again, so we have to make sure that our eta is chosen so that the difference in the objective function is small. Okay, so I'll let you figure this out. I mean, you have to choose k large enough so that this quantity is so small that it makes no difference. And then this x tilde minus xk. Sorry, what did I write here? Yes, so something wrong. I'll correct this. This probably is wk minus xk or something like that. Yeah. Anyway, so the difference to the objective function is very small, and things work out. But that is just a detail that you're used to. This is where the argument is. Okay. So please read the book and figure this out. One last minute. The final, there is a way. Sorry. So if there was any question, please ask. I don't know why. Questions? After this, what I want to do is in 1 minute, just state the. So after this, I just want to state the duality theorem and stuff. Okay. So there is a way of generating duals for cone programs, which is a recipe. If you think about it, this is what you would come up with, because we write our cones, our constraints in this funny way. We have to write the duals here, yeah, and the dual cones show up in the dual of the cone program. And here you wrote B minus AX. Here you write A transpose minus C, and that is because we have written it as a minimized program. Yeah, don't worry about it. Because
so,
you remember,
I had not yet defined dual cones actually.
Okay, you've not. Doesn't matter. There are objects called dual cones. Yeah, and then there is a way of constructing from a cone program, just like LP duality. There is a recipe for going from a cone program to its dual cone program. Yeah, and then one can ask, what is the relationship between the object? And the theorem is this: if the primal is feasible, it has a finite value and has an interior point, and that is why we did all this. Okay? All this was done because we wanted to leverage it. So it has an interior point x tilde, then the dual is also feasible and has the same value. This is the strong duality theorem of cone programming, which hopefully you will see next time. Okay, so yeah, I will correct whatever errors I have made. I might put in more explanation for the why the objective function doesn't change too much. I did not argue it very carefully, and you will find it on in the notes. But read the book. Questions? All right. So thank you very much. Gone over time again.
Thank you, Jacob.
Thanks.
Thank you, sir.
Sorry, you had a question, Yashu.
No, I said thanks.
Thank you.